All right, I got 10-10. Let's go ahead and get back into it. Any questions about anything before we jump back in? I think the next thing that's due is it 8-5 that's due on Sunday? 8-4? Okay. All right, so we're on 8-6 right now. So I think it looks like we left this example kind of in the middle. So let's reset the stage a little bit. Basically what we're doing now is if I give you a function, we can represent that as a power series. So basically, even though this function I've given you here is very much not a polynomial, we have tools to represent it like this. It's like a polynomial, but it has an infinite amount of terms. So it looks like by the time we left last time, we had figured out what that power series was. Now I want to figure out where that thing converges. So how do we build this power series? It looks like we're treating this as the sum of a geometric series, which right now is kind of the only avenue we have. So this function is 1/1 plus x squared. And from there, we can kind of pluck out what the first term is and what the common ratio is. So now that we have that power series, what can we do to figure out where it converges? What values of x it converges on? Ratio test is typically the first thing to try. So what's the limit I'm looking at if I look at the ratio test here?
X squared plus 1 over negative x squared.
The absolute value of that, right? Can I simplify this at all? The absolute value of negative x squared. And this is going to be less than 1, right? So what happens to the limit here? Yeah, so the limit, what is the variable as far as the limit's concerned? Like to look at this limit, what am I wanting to increase? N. N is gone now. So the simplification just left us with the absolute value of x squared. So really all I have is this. Not really a limit anymore, but what I do have is x squared is less than 1. What does it mean for x squared to be less than 1? Is that all? And greater than -1. So basically, absolute value, I'm not sure, maybe you've seen this before, but one thing I've seen for absolute value is this. The absolute value of x is equal to the square root of x squared. Which just might seem a little strange to think of it that way, but when you square something, you make it positive. And to undo whatever you did to the magnitude, you can take a square root. So not exactly a coincidence that this square follows the same, kind of gives you the same result that the absolute value does. So far, what I have for my interval convergence is from -1 to 1. Do I need to look any deeper than that? Or can I just say that this is my interval? I can. So let's test one of them. If I plug in -1, then what does my series become? Should be -1 to the n, right? What does that do? Diverge. Basically, it's just going to bounce back and forth between -1 and 1. But in general, we don't even have to test. And let's talk about why. I don't have to look at the endpoints. Think about the way we're setting these up. For basically to turn that function 1/1 plus x squared into a power series, what kind of series did I kind of treat that as? It's a geometric series, right? For a geometric series, something we've already talked about is the endpoints never converge. So for a geometric series to converge, I need the I need the ratio to be strictly less than 1, or between -1 and 1. So because of that, the endpoints are never going to converge. So basically, when we build a power series this way, after we get the interval, we can essentially call that done. We know the endpoints are not going to converge. How we do? Okay. Can we turn this thing into a power series? So remember that right now, the only weapon we have really is to turn this thing into a, or to treat this as a sum of a geometric series. Can we make this function fit this template? How so?
It's,
A is gonna be 1. Are we sure?
it's right.
I don't think we can. So I don't think this definition fits that just yet.
A 1/2
How'd you get that?
multiply the numerator and denominator by 1/2, so I could get x plus 1.
So basically,
To 1 minus r.
something that we haven't really, yeah, we didn't really point this out last time, but we didn't really pay attention to this 1. But that has to be there. So let's do some kind of re-expression here. This is 1/2 plus x. So yeah, from there, it might be tempting to say, yes, the first term is 1. The common ratio is -x. But we can't really do that yet. So the way Caleb is putting this, yeah, Caleb, will remind me what you said again?
Multiply the numerator and denominator by 1/2 to get 1/2 over 1 plus x over 2.
So if I multiply numerator and denominator by 1/2, then I get 1/2 over 1 plus x over 2. Is it legal to do that? Or in other words, am I looking at the same thing, just written a different way? Go ahead.
I understand you can do it, but can you explain why you're doing it?
Yeah, so it's a good question. I'll put it back on you. Why is, so not only is this legal, I think it's necessary. So why is it necessary to make that manipulation? Right, so this, right now, the only real recourse we have is to treat these series or treat these functions as sums of geometric series. And yes, we can get the first term and the common ratio if we like kind of fit this template here. But one thing that's required is to have a 1 in that position. So basically, you're gonna have 2 terms in your denominator, one of them needs to be a 1. So the fact that we started off with that not happening is why that's necessary. So now that we've made that manipulation, can I now treat this as a geometric sum? If so, what is its first term and what is its common ratio? 1/2 is the first term, common ratio is -x over 2. So now can we build this power series from that? Yeah, sure. Where does the ratio of -x over 2 come from? The r, but how did you, so that was, I think you said this, how did you know the r was -x over 2? Right, so looking back to our sum of a geometric series, it's always the first term divided by 1 minus the ratio. Let's rewrite this one more time. Let's factor out a negative sign. So now I really have, now this even more closely fits this form up here. I have my 1, but I also have 1 minus. which means now I can directly read the first term of the common ratio from it. Oh, so like, how did we actually write this? I think that came directly from Caleb's suggestion here. So here's what we were given. I need to get this 2 to be a 1. So basically multiply the numerator by a half, multiply the denominator by a half. So doing that, basically this is 1, right?
So that has to be 1, if we're using the.
Yeah, it has to.
Has to be 1. Okay, I almost my problem. Take it the 2 to 1.
Yeah, so basically this,
Oh, and then you have the x over 2.
yes.
Oh.
So the whole motivation of this 1/2 over 1/2 was to make that 1 show up where we wanted it.
Okay.
Good question. So for us, we know that a is a half. We know that r is negative x over 2. We start building out some terms. The first term is what? 1/2. Next term? And then?
Or x squared over 8 positive x squared.
So what's happening to the denominators here? They're doubling. And the powers of x? They're incrementing by 1 each time, right?
Are you using the square?
The square?
Yeah.
On the third term? Good question. How do I get x squared over 8? Yeah, so basically, these are geometric series, which means that if you know what that common ratio is, you can use it to basically populate everything. So once we figure out that common ratio and the first term, I guess I'll ask Caleb, since I think he gave out the first 2 terms. How'd you know that negative x over 4 was the second term in the sequence?
Yeah, just multiply 1/2 by negative x over 2.
Right, so basically let the common ratio govern everything. It has to. Can we condense this now?
X over 2 to that power.
Negative x over 2 to the power of n. Does this work? If n equals 0, what's the first term? It should just be 1, but that's also not okay. If we put a half in front, so 1/2 times negative x over 2 to the n. So if n equals 0, that'll come out to a half, right? What about if n equals 1? Okay, so it's starting off right? Is it a coincidence that what we have is basically the sum from 0 to infinity of a times r to the n? Was that? No, not a coincidence at all. So, and especially it makes it, the fact that we're counting from n equals 0 makes this simpler to deal with. Because basically your first term is going to be, or if n equals 0, what happens to this thing always? It goes to 1. So basically you're left with the first term. Something?
Is it always being put back?
Yeah, this is not a coincidence. As long as what? So the thing the caveat I really want to give here is, as long as you are counting, like the first value of n is 0. Otherwise, you have to kind of account for that offset. Yeah, but typically you have freedom to define it however you'd like. All right, radius of convergence or interval of convergence. How should we find that? That's what I was hoping would happen. So, like I said, typically the ratio test is kind of the thing that gives you your, like, where your series converges. But let's rely on the fact that we're basically dealing with a geometric series. And what do we know about geometric series? They converge when the absolute value of R is less than 1. And we know that our value of R is negative x over 2, right? So from here I can say this, -1 is less than x over 2, which is less than 1.
Absolute value. You have to put the negative there.
Or it would mean like from here to here, I remove the negative and the absolute value.
Yeah, you're just trying to absolute value.
Yeah, you can take the negative off.
So
What's that?
you have to keep the negative on the x over 2 to have that -1.
No. Well, I mean, this is true. The absolute value of negative x. Actually, I guess it's not true. Well, this is though. The absolute value of negative x is equal to the absolute value of -1 times the absolute value of x. Which means the absolute value of negative x is the same as the absolute value of x. So why don't I put one more step in here? If I have the absolute value of negative x over 2 is less than 1, then that means the absolute value of x over 2 is less than 1. Is that fair? And then from there, I'm going to remove the absolute value and give myself that 3-branched inequality. So -1 is less than x over 2, which is less than 1. Can I get a interval of convergence from that? So yeah, multiplying through by 2 gives me -2 is less than x, which is less than 2. What about the endpoints? What's that? We don't. But how come? Geometric series. I know that for a geometric series, these are hard boundaries. Always. Meaning that you will never have convergence at the boundary. It has to be strictly less than 2, or strictly between -2 and 2. Go ahead.
I'm assuming that only works if we treat it as geometric.
Yeah, so this right here, and I'll make a note. I mean, the general form of a power series is much more complicated because there's a lot less restriction on them. But this right here is purely a geometric thing. In a general power series, you can talk about the first term in a power series always, but most power series don't have this R. Like, what does this R stand for? Common ratio. Most power series don't have that. Geometric series always do. Thanks for pointing that out. What else? All right, moving on. What can I do here?
Similar to the class problem, because there's a 2 in the denominator.
Yep. Okay. So what would you like to do?
Multiply by 1/2 again.
Yeah. So basically multiply by 1/2 over 1/2. That gives me what? X cubed over 2 over 1 plus x over 2, right? And let's make it really clear what all the pieces are. 1 minus negative x over 2. So it sounds like you're seeing some similarities between this one and the one we just did. So what does this one have in common with the previous? The denominator is the same, which means what else has to be the same? Common ratio has to be the same. What's different? Which means the first term what?
First term, like, do you use the X, first term, like, X.
The first term can be, we can have an x in it, that's fine. Because I want to point out here, when we build up, you know, one of the things we're going to come up with here is this power series representation. When we use like this sigma notation to construct a series, what's the variable on this notation here? And so the x, as far as the way this power series is built, that n is, or the n is the variable, the x is a constant. Yeah, so I mean, we said a times r to the n was always going to work for us. If that's true, then this should be the power series, right? What's the difference between this thing and the thing we just looked at? Starting value, right? But really, I think I can rewrite this. This is the same as x cubed times 1 over x plus 2, right? So basically, this function is exactly the same as the last one with x cubed multiplied by it, right? If that's true, then this power series should look exactly like the other one, except with that x cubed multiplied by it. Is that true? Didn't box it in. Is that the only difference between the sigma notation that I circled in here and the one over here? Yeah, that should be the only difference. So basically, so because of that, you can rely on a lot of commonalities here. We had the same common ratio. And really the first term was like a multiple of the other first term. We can just multiply this thing by x cubed. Can we also say what the interval of convergence is? Should be the exact same thing. How come? Common ratio is the same. What's that?
How did we?
Yeah, in fact, I'll just go back to the last example. Because we would find the interval the same way. To find the interval, you first have to figure out, I guess, the radius of convergence. How do we find the radius of convergence on this example? Or I guess, yeah. From the what?
We can give the absolute value of manufacturing to, that was just awesome.
Right, so in a geometric series, the common ratio is enough to figure out where this thing converges, or to figure out the radius. So our common ratio is negative x over 2, which means the absolute value of negative x over 2 has to be less than 1. So that same calculation, because we have the same common ratio in this next example, we're going to have the same radius. So basically we have absolute value of negative x over 2 is less than 1. That means that absolute value of x is less than 2, which leads to this. Questions? All right. Moving on. So pretty much everything we've dealt with so far, the only hope you had of turning a function into a power series was through that geometric sum, the sum of an infinite geometric series. We're going to bring in derivatives and integrals to kind of give us some more paths to get there. So one thing I want to point out here is if you have a power series. So what I've shown here is generic power series. So basically some list of coefficients multiplied by this like incrementing powers of X term. Does a power series have to have a radius of convergence? So I mean, it might, so remember, we have kind of three cases. Everything we've looked at today has a finite but non-zero radius of convergence. There are some values of X for which it converges. But in general, what we can have is that maybe it only converges at that single point A. Maybe it converges absolutely everywhere. But if it has a radius of convergence that is a real finite non-zero number, then that power series converges, basically the derivative converges on the same X values. So we didn't do it, but any of the series we just found, we could take their derivatives. And if we did, those things would converge for all the same values of X. Actually, I can take it back. It'll have the same radius, but one thing we can't say for certain is that the interval holds. So what's the difference that might be there? How could the radius be the same, but the interval be different? So let's just look at the last two examples we looked at. So we had -2 was less than X, which is less than 2, right? In that situation, what's the radius of convergence R? 2. The center value of X is 0, and I can be 2 units away from that on either side. Is there a way for this interval to be different, but still have the same radius? So yeah, you could change where the center value is. What's another way? Maybe we have to include one of these endpoints. So that's something that might happen when you take a derivative or take an integral, is that even though the radius is guaranteed to be the same, you might end up getting convergence at one of the endpoints. So in general, with a geometric series, you don't have to look at the endpoints, but after you take a derivative or an integral, you might.
Will the center point be the same or will the center point change?
I don't think it will. So my instinct is that it's impossible for the center point to move. But I don't feel good enough about that to say it will never happen. But I highly suspect that it can't. It can't move. So let's talk about this in general. If this is a very generic power series, can I find its derivative? How should we go about doing that? Yeah, what would that look like? What would that look like?
X minus it. To the N minus 1.
And then, so is that what you're saying?
Yeah, I think, and then we have to multiply it by X, right? Or, well,
You have to multiply by.
Is A.
So here's the thing, I'm asking for f prime of what? So so the way you attacked this, Bella, it seemed like you were treating n as a constant and x as the variable, which I think is consistent with calling that f prime of x.
Yeah. I'm confused on what's like a constant and what's so.
Yeah, and that's totally valid.
But like that's.
This is X.
What's that?
It says F prime.
F prime of x, which means, and we got two different things going on here, right? Because if I was asking you about this sum, then what's the variable? N, but I'm asking about the derivative, which is, that's a function of x. So do we think this is the correct derivative for the thing I gave you? Okay, so let me try to convince you a little bit, because this is actually, which N?
And right, see it.
Where'd that come from?
Oh.
So let's look at, probably the first derivative rule you ever learned was this one, right? The derivative of x to the n. But that's okay, there's all kinds of other stuff confounding it, so you can't see this thing in there. But what's the derivative of x to the n? Right, so that, hopefully you can see that in there. Bella, you also said you wanted to multiply this by x.
Well, you have to multiply by the derivative of the inside function.
What's the derivative of the inside?
I guess one, right, because A is a constant.
Right, so you're right to pay attention to the chain rule, but in this case,
It's just one.
the derivative of the inner function is 1. So because of that, let's hold on to this. One thing I want to do to maybe make this a little more convincing is, let's actually build out some terms. What's the first term of this power series going to be? Cn. Well, C0. Because when n equals 0, I'm going to get C of 0 times 1, right? And then plus C of 1 times what? X minus a. Plus C of 2 times x minus a squared. And I'll do one more. Plus C of 3 times x minus a cubed. So this is basically a polynomial, right? I've just got a bunch of terms all added together. Can I find their derivative? What's the derivative of C0? 0. What's the derivative of C1? Or the C1 term? C1, right? What's the derivative of the next one? 2C2.
Or X minus A.
X minus a. Plus 3C3 x minus a squared. Do these 4 terms fit the thing Bella gave us? When n equals 0, I get 0, right? When n equals 1, I get C1 times x minus a to the 0. And so forth. I feel better about it now. This is actually a first for me. Every time I've gone over this, people have kind of elected to write out the first few terms and then take a derivative of those, and then we kind of recompact it. But one thing to point out here is, very obviously, because we saw it done, you can go straight to differentiating the terms that build up that sum. And the thing to pay attention to is basically, depending on what you're looking at, so there are two big things to look at here. One is what we've been looking at for a while, is how to build out this sum. And the variable there when you're constructing that sum is n. But now that we're talking about derivatives, we're not taking a derivative with respect to n, you're taking that derivative with respect to x. So basically, certain things are fixed and certain things vary when you're looking at from different vantages. So it's important to keep track of that. How we doing here? If that's the derivative, then how do I do this? Just like that. So I mean, if in the last example, if we're able to differentiate basically any nth term in that sequence, we can integrate the same way. Do we still have plus c?
Or like plus. Well, yeah, plus C.
That's a good thing to think about. Let's figure it out. It's not a definite integral though. Maybe let's look at the first few terms there. So if I know that, again, f of x is equal to c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a to the third. What's the integral of c naught? C naught x minus a plus
C1 x minus a squared over 2 or C1 over 2.
Yeah, I'm just- so basically you're gonna all look at this c2 over 3 x minus a cubed plus c3 over 4 times x minus a to the fourth. But is there going to be like some mystery constant here? I'll call it capital K. I think there will be, but I think it exists outside of this sum. The meaning that I'm not adding that K every single time.
It's just-
Basically, there's a sum that builds up basically all of this stuff. But because there is some kind of arbitrary constant, I don't know if I can include it in the actual summation notation. I'm not adding it with each successive term.
I mean, how do you know that though, based off of this, you just, some of the list.
So here's the thing. When I integrate c naught, I get c naught times x minus a plus an unknown constant, right?
Yeah.
When I integrate c1 times x minus a, I get an unknown constant, right? Are those unknown constants the same as each other? No, so basically here's a cheat we do in like with integration all the time is if we have a bunch of those, like a bunch of constants whose values we can't know all added together, we kind of just blob them all together and call them a single constant. So that's what I'm doing with that K there. So I have all these arbitrary constants that I know absolutely nothing about. But if I add them together, it's still going to be an unknown constant. It's just easier for me to treat them as a single thing. It's usually C, but you can call it whatever you want. I just didn't want to use C because we already used it. Question.
What is chaos in the parentheses for your answer?
That's what that like amalgamated like unknown constant is. That's the best I can do. I don't know. I don't have any more information to tell you what it might be. But we just have to acknowledge the fact that it might exist. Need a lot more information. Questions?
Will we ever have to solve for them?
I'll have to give you information to get it
Okay.
if I ask for
I
it.
just remember in council when we had to solve for what C is sometimes.
Right, but what information do you need for that? So like, let's give you a typical Calc 1 question. If f prime of x is equal to 3x plus 2, and I ask you for f of x, yeah, I mean, typically what I'll give you is like, all right, well, f of 0 is 5. So I have to give you some data. Yeah, if I ask for it, I'll have to give you some more information. What else? Go ahead.
This is on the test, do we test it?
I'll say no. I'm more interested in the summation. I mean, really, if I'll have to give you the means to figure out what that constant is if I'm actually worried about it.
Let's see.
Usually it tells you. I know in the like early on in the semester, it would either give you the plus C kind of outside the text box, or it would tell you not to worry about it. Basically, follow suit with whatever it tells you. So here's a kind of I think we've looked at this exact function before. And I think we've also found, let's just hold off on that. I know we've dealt with this exact function. Because of that, we might have some idea about how it converges, but now I'm asking for its derivative. Is the derivative something I can take? You have to use quotient rule.
Everything else is a constant, so that's the
Oh.
2n.
So-
2n times 6, 2 minus 1 times that.
Yeah, so basically, where's the variable here? Right there. So yes, the quotient rule would work. I think it'd be a lot to keep track of.
Which was the n in the denominator. Constant.
Yes, how come? Because of the what?
Yeah,
Yeah, so the factorial is, that's, I mean, that is something that varies, but what's the variable as far as that factorial is concerned? And we want to find a derivative with respect to what variable? Which means the only thing, so basically we have two symbols here, right? N and X. But they're not variable for every situation. When we're looking at a derivative, what's the only variable we're allowing when we take a derivative? X, which means we want n to be fixed. So basically, we're going to find a derivative where the only thing we're allowing to vary is x. Which means we can take this derivative. Let's just do it. We've talked about how to do it, but let's put it in action. The only variable is x, right? So what's the derivative of the numerator? So for now, I'm just going to copy down the -1 to the n. That's a constant. As far as the derivative is concerned, that thing is fixed. And then I have 2n times x to the 2n minus 1. All over what? The denominator totally unaltered.
so you're gonna find. Because that.
I'm only finding the derivative of the numerator is kind of a coincidence, but what am I really only finding the derivative of? The x terms. If there was x terms in the denominator, I think we would have to do quotient. But I believe this is our derivative.
So then they could have the x part of the derivative because it's like multiplied by the x.
Yeah, it's a constant multiple. So basically, it's the same reason that, what's the derivative of 5x? It's equal to 5, which is the same as 5 times the derivative of x, right? So same kind of thing here. Would it be helpful if we wrote out some terms and took them derivative term by term to show that this actually works? So what's f of x? Let's write the first few terms out. What's the first term of this power series? One times, is it just 1? Someone double check me. I think -1 to the 0 is 1, right? X to the 0 is 1. 2 to the 0 is 1. 0 factorial is 1. Okay, so the first term is 1. What's the next term? Minus something. Minus x squared over 2 squared times 1 factorial squared, right? So 4. Hopefully 3 terms is enough, so I think I can see this thing getting hard to deal with very soon. So next term will be x to the 6th or 4th. X to the 4th over 2 to the power of what? 4, which is 16. Times 2 factorial squared, so 4. Do we agree with those 3 terms? Can I take derivatives of those? What's the derivative of zero, of one? Just give it away. What's the derivative of the next one? Minus x over 2 plus x cubed over 16. So now let's make sure that our formula actually agrees. If n equals 0, what do I get? It's actually going to be 0.
2 times 0 numerator.
Oh yeah, there's n in there. Okay, yeah, then yes. So I forgot about that 2n there. So first term fits. If n equals 1, what did our derivative give me? -1 times 2 times x. So we get -2x in the numerator. And 4 in the denominator. So that also matches. So yeah, no matter which way we went out this, term by term or all at once, I think these things agree. How we doing? All right, so now we only got a few minutes left, so we'll get as far as we can here. So I'll write out the thing we keep relying on here is the sum of an infinite geometric series. First term divided by 1 minus r. This function f that I gave you, can we treat it like the sum of an infinite geometric series? Take the what? You take the square root, you're making a brand new function. So
Factor it out. Minus 2x minus or plus x squared.
oh, so you can, if you expand this, you'll have f of x equals 1 over 1 minus 2x plus x squared. Does that fit our geometric series? How so?
Just make 2x plus x squared power.
I actually don't know. Obviously, it's not what I intended, but I'm wondering if that actually works. I'm gonna figure that out later. So let's go towards what I intended here. So we just kind of talked about like starting. What we started with on Wednesday is if you can make your series look like the sum of a geometric series, or if you can make your function look like that sum, you can write it out as a power series. Now we're bringing in calculus to maybe give us some more ways to get there. Can I take a derivative of something that looks like 1 over 1 minus x squared? What is that something? We'll call it g. Or better yet, let's not guess. Can I integrate 1 over 1 minus x squared? What is the integral of this? Hopefully you'll see after we do it.
X.
To the -1, right? Over -1. And then kind of got to obey chain rule as well, right? So I'm going to divide by the derivative of the inside function. So I think the integral of 1 minus x to the -2 is what? Conveniently 1 over 1 minus x, right? So here's something I have just found out. The derivative of 1 over 1 minus x is 1 over 1 minus x squared. Do we agree with that? Is the thing on the left something I can turn into a power series? Not only can we, I think we've done it a few times now, right? Is 1 over 1 minus x a geometric series? What's its first term? What's its common ratio? Which means I think we can write it as the sum from n equals 0 to infinity to of this, right? X to the n. So
Could you separate the f of x into two different functions, like one over something and then the one over something and then do it separately, or can you not do that?
how would you separate it? Like into what things?
I don't know, like, work to be able to do that?
In general, you can. So now that you're mentioning, I think you could split this up into 1 over 1 minus x times 1 over 1 minus x. I think that works too. But then if you break those both up into like polynomials, what happens when you multiply those polynomials by each other? You can't just do it like power by power, like you have. I'll give you a. If I do a plus b plus c times d plus e plus f, how many terms does that come out to be? That'll give you 9 terms. So that multiplication gets nasty in a hurry. Let's go ahead and stop here. I'm already over. But we'll pick this up more about how to bring calculus into this, or how to bring derivatives and integrals into this process next time.